In our study of trigonometric functions so far, we've talked about them as functions of arc length, meaning we need to put an arc length into them, and then we get a ratio of the coordinate to the radius out of them, right? Arc length, great. It's a little awkward to talk about around the edge of the circle, and we've done a little bit of work with angles, so the question is, could we use angles instead? And well, I'm asking the question, you're probably like, yes, Professor Bry, we probably can, right? And your previous experience with trigonometric functions, if you have any, oftentimes we use angles instead. So here's how we kind of go from the arc length definition to an angle definition. We remember that the arc length formula, when we encountered it, it was defined as S is equal to R theta, where S is arc length. So in this case, we had T is equal to R theta, okay? But on the unit circle, remember that R is equal to 1. So then we get T is equal to 1 times theta, meaning that T is equal to theta on the unit circle. Okay, so now just to be clear, what does this mean? T is arc length, and theta is our central angle. Okay, so upshot is wherever we are writing functions of t of arc length, we can actually write those as functions of theta being the central angle on the with trig functions. So that's kind of neat. So we can actually rework our definitions. Granted, noticing that really the only thing that is changing is we have theta everywhere instead of t. Okay, the other side, the ratios that we have, y over 1 for sine, x over 1 for cosine, y over x for tangent, those remain unchanged. It's just changing domain elements. Okay, so just be aware that also when we talk about theta, theta is the central angle, right? So when we're looking at the unit circle, I'll just draw a quick little sketch here. Okay, if we have, you know, t being from 1, 0 over to this point P, and then t is along there, right? Then theta is the angle here from the positive x-axis up to the terminal side where P intersects the unit circle. Okay, so just be aware of that. So all we need now is an angle, right, whose terminal side passes through P of xy on the unit circle. So there are some other interesting things that come out of this. Rather than us being given the point on the unit circle that intersects, or that intersects the unit circle with the central angle, we can actually find that point. So now the question here is, at what point on the unit circle, blah, blah, blah. Okay, so I need a picture. Unit circle. Okay, central angle of pi over 4. Okay, if we remember, this is 0, this is pi over 2, so pi over 4 is going to be right about here. Okay, so I'm saying that this is pi over 4, and I'm wondering what point. So I'm looking for this x and y coordinate. Okay, so now how in the world do I do this? Okay, here's what I notice. If I have theta is equal to pi over 4, okay, that is perfectly along the line that splits this quadrant, right? Because it's halfway between pi over 2 and 0. Okay, this line happens to be the line y is equal to x. Okay, so I know y is equal to x, and I know that this point xy is on the unit circle. The unit circle has the equation x squared plus y squared is equal to 1. But I just said that this point is on this line y equals x, so instead of writing y, I could write x in its place, and well, it would be squared. Simplify 2x squared is equal to 1, and then divide both sides by 2. So I get x squared is equal to 1/2. Square root both sides. When I introduce a square root, it's plus or minus, or I need to include a plus or minus 1/2. And so this, if I simplify this, this is plus or minus square root of 2/2. Okay, being that I'm in the first quadrant, that means x is positive square root of 2/2. And this would also be the same value as y. Okay, so in total, if this is my point P, P of xy is square root of 2/2, comma, square root of 2/2. Okay, so now I can identify an angle, a central angle, with a point on the unit circle. That's kind of neat. Okay, turns out you can do something similar for angles that are multiples of 30 and 60. And with that, you can actually complete the first quadrant. Okay, so we know that this point, if this is, pi over 4, actually, let me label it here. So this angle here is pi over 4, which is 45 degrees. This has coordinates, square root of 2, I'll zoom way in. Square root of 2/2, comma, square root of 2/2. And then the other angle, so if this was a 30-degree angle, which, oops, undo that. Let's just scribble that out. So up here, this is 30 degrees, which is pi over 6. We actually find that this point here, it can be represented as square root of 3/2, comma 1/2. And if this is pi over 3, which is 60 degrees, then this point here is 1/2, comma, square root of 3/2. Okay, and now these three lines here are very nice angles that we can work with. And in fact, we know quadrant 1, if you do reflections across the x or y axis respectively, you can complete the whole unit circle, which I did a quick Google search and found this PDF. I kind of like this angle, or this picture, because it has the angles labeled. I would like them labeled in radians too, so if you wanted to label them as, like, pi over 6, pi over 4, pi over 3, you could, but you at least know the important angles along the unit circle and their coordinates. So I cannot stress enough, memorizing this is going to be super helpful to you. If you have trouble with memorization, at least remember to look this up and verify this, but I promise you, you're going to use this stuff so frequently, you're probably sure to memorize it one way or the other. Okay, so we will get some more practice with this stuff going forward, but again, unit circle is developed all using trigonometry, where our functions are functions of the central angle theta.